Assalamu alaikum. I welcome you to the 38th lecture for the series of lectures on advanced computer architecture. Today, the focus of our discussion will be the storage devices and input-output systems. After a brief review of what we have been talking about the multiprocessing, we will discuss what are the storage systems and how input-output devices can be interfaced with the microprocessor. In the last 4 lectures, we discussed how the computer performance can be enhanced by using parallel architectures. Here we said that the parallel architecture is a collection of processing elements that cooperate and communicate with each other to solve a larger problem faster. The parallel architectures are implemented by using single instruction, single data stream, single instruction, multiple data stream, multiple instructions, single data stream, and multiple instructions, multiple data stream machines. We have noticed that the multiple instruction, multiple data stream or MIMD machines facilitate complete parallel processing. The multiple instruction, multiple data stream machines are classified as the centralized shared memory architecture and distributed shared memory architecture. The centralized shared memory architecture maintains a single centralized memory with uniform access time, whereas in contrast to this, the distributed shared memory architecture has non-uniform memory architecture, but it offers greater scalability. The sharing of caches for multiple processing also introduces some problems. In these problems, the most prominent problem which we discussed in detail in our earlier lectures is the cache coherence problem. In centralized memory architecture, the cache coherence problem is resolved by using different techniques such as write validation and broadcasting. And these schemes are implemented by using snooping algorithm. Whereas in distributed shared memory architecture, the cache coherence problem is resolved by using the directory-based protocols. With this much discussion onto the parallel processing and our earlier discussion considering the performance enhancement using different methods, we have to look into what is existing outside the processor and how the outside of the processor is affecting the overall performance of the system. Today, the processing power of a central processing unit is going to double every 8 months. The memory size is also getting doubled after every 18 months, and the secondary storage devices such as the disk. In the disk, the positioning rate is also getting doubled after every 10 years. But the effect of the performance of the secondary storage like disk is very much prominent onto the overall performance of a microprocessor based system. If we recall from our second lecture, where we discussed that the quantitative principles to define the computer performance, and at this stage we noticed that the execution time of the central processing unit is not the only parameter to measure the computer performance. Rather, the overall performance of a computer is measured by its throughput, where the throughput is very much influenced by the system which is external to the processor. As we have already pointed out in our 25th lecture, that measuring the overall performance of a powerful uniprocessor system or a parallel processing architecture without considering the impact of external devices is just equivalent to talking of the performance of a very sophisticated car which is not fitted with any wheels. So you can well imagine what will be the performance of such a car which may have very powerful engine, but it does not have any wheel. So its performance on the road will be zero. So this shows that the effect of neglecting the IOs on the overall performance of a computing system can best be visualized by taking into consideration the Amdahl's law, which identifies that the system speed up is limited by the slowest part. Now, in order to explain this, we can consider an example of a computer and where we can find the response time, and if we have to look into the overall performance speed up of a computing system, where if the response time is 10% longer than the CPU time, then in this case, if we assume that the CPU time is speeded up by a factor of 10, and if for the time being we neglect the IOs, then the overall speed up as determined by using the Amdahl's law will come out to be equal to 5. That is, it is half of what we would have achieved if both the CPU time as well as the input output devices time was speeded up 10 times. In other words, we can say that 50% loss in the speed up is there due to neglecting the impact of the IOs. Similarly, if we assume that the CPU time is speeded up by 100 times, and again if we neglect the impact of the IOs, then the overall speed up is 10. That is, there is 10% of what we would have achieved if both the CPU time as well as the IO times were speeded up 100 times. So in other words, we can say that in this second example, we have got 90% loss in the speed up due to neglecting the IOs. The IO performance increasingly limits the system performance as well as its efficiency. So, after having a detailed discussion on the performance enhancement of the central processing unit by using the performance enhancement in the instruction set architecture, by proposing new computer hardware to enhance the CPU performance enhancement, then also after talking about the methods used to achieve the instruction level parallelism and the impact onto the memory design, and then we discussed different memory hierarchy systems to enhance the overall performance of the memory system and hence the performance of a CPU. And then at the end, in the last 4 lectures, we discussed using the parallel processing technique to enhance the performance of a microprocessor. We are now in a position to focus our discussion onto the study of the systems which are outside the processors, and we call these systems the I/O systems. Now today I will take up different types of I/O systems, different attributes of I/O systems, and we will see how we can enhance the overall performance of a system by enhancing and developing different types of I/O systems. An I/O system comprises storage I/Os and communication I/Os. You can see a complete computing system from this diagram, where you can see that a processor, and if there is any external cache, they are connected to the memory, to the external storage devices such as disk or some network or some I/O controller through different devices. And now we are going to discuss what are the impact of different storage I/Os and how these storage I/Os communicate with the processor and how a communication I/O can be developed. The storage I/O consists of secondary storage devices and primary storage devices, whereas the communication I/O consists of the I/O buses which interconnect the microprocessor and memory with the I/O devices. Today, the major focus of our discussion will be the storage I/Os. As you know that the secondary and primary storages include the magnetic disk, the magnetic tape, automated tapes, libraries, CDs, and DVDs, etc. These devices offer bulk data storage, but on the contrary, they are too large for embedded applications. Here you can see the technology trend from this graph, where you can see that there has been an extensive improvement in the disk capacity during the time from 1971 up to 89. Here you can note that before 1990, the disk capacity has been getting double every 36 months. However, the technology has improved to an extent that after 1990, the disk capacity is getting doubled after every 18 months. This improvement in the technology is basically driven by the prevailing computer paradigms. As you know that in 1950s, the computers observed migration from batch processing to the online processing, whereas in 1990s, they migrated from online processing to the ubiquitous computing. The ubiquitous computing is one where the computer is placed in phones, in books, in cars, in videos, in cameras, etc. Moreover, it started getting used in nationwide fiber optic networks with wireless communication, etc. This development in processing basically affected the storage industry also, and it motivated to develop some smaller, cheaper, and more reliable with small power consumption embedded storages for ubiquitous computing systems. Moreover, at the same time, for data utilities, the high capacity, hierarchically managed storages were developed. Now, before discussing the storage technologies, let us perceive the historical perspectives of magnetic storages. The era of 1956 to the early 1970s observed that the mainframe computers, they employed the priority interface. Moreover, there was a steady shrinkage in the form factor, that is from 27 inches disk to 14 inches disk. Whereas during the time 1970s, the developments were such that you can note this disk history from this diagram, which shows that in 1973, the capacity of a disk was up to 140 megabytes with the density of 1.7 megabits per square inch, whereas the technology improvements resulted in 2,300 megabyte disk in 1979 with the density of 7.7 megabyte per square inch. The era of mid-1980s observed the voyage of computing from first generation to the client-server computing, and this era resulted in the end of the proprietary interfaces, and it gave rise to the acceleration in downsizing the disk. That is, the disk was downsized from 8 inches to 5.25 inches. The industry standards such as SCSI, IPI, and IDE were introduced, whereas the era of late 1980s up to the early 90s was the era of laptops, notebooks, or palm tops, etc. Here, in these type of computing systems, the 3.5 inches, 2.5 inches, and up to 1.8 inch form factor disks were introduced. Furthermore, the challenges by the enhancement in the DRAM and introduction of the flash RAM were also there. It is quite obvious from this figure over here, which shows that in 1989, The disk storages had the density of 63 megabits per square inch with the disk capacity of 60 gigabyte, but at the same time the size was too huge. However, in 1997, the disk, which may be referred to as the palm disk or which can be taken up in a palm, it was introduced. These disks has much higher density, that is 1400 up to 3000 megabits per square inch, and its capacity was also in the range of 2300 up to 8100 megabytes. Now, with this much introduction to the historical development, let us have a discussion onto the magnetic disk. The purpose of introducing the magnetic disk was to have a long-term, non-volatile storage with large, inexpensive, slow level in storage hierarchy. The characteristics of a magnetic disk are that it has got seek time in the range of 8 milliseconds, and it have positional and rotational latency, which is relatively small. The transfer rate about a sector per millisecond, and it is having a capacity in gigabytes, and it is getting quadruple every 3 years. Here you can see the design of a magnetic disk. You can see that it consists of a number of platers. These platers are arranged one above the other, and each disk is formatted and it is divided into tracks, and the tracks are further divided into sectors. However, the performance of a disk can be determined by determining its response time, where the response time is one which is measured from the time to queue the information and the service time of the disk, where the service time of the disk includes the controller time, the seek time, rotation time, and the transfer time. Another type of secondary storage is a magnetic tape, where a magnetic tape uses the same technology as the hard disk, but in case of hard disk, the disk head flies above the surface, whereas the tape head lies on the surface. The disk is fixed, whereas the tape is movable. With this much discussion onto the storage devices, let us talk about the parameters which may be used to identify the performance of IOs. The basic parameters are the diversity, which identifies which IO device can be connected to the central processing unit. The capacity defines how many IO devices can be connected to the CPU, whereas the third parameter is the latency, which gives us the overall time to complete a task, and the fourth parameter is the bandwidth, which gives us the number of tasks completed in a specified time, and this is usually referred to as the throughput of the system. The parameter diversity refers to the IO devices and capacity. It identifies how many I/O devices can connect to the CPU. Here, note that the I/O performance measures have no counterpart in the central processing unit matrix, because here the parameters are different as compared to the parameters for the performance measurement of a CPU. Furthermore, the latency, which is the measure of the response time, and bandwidth, which identifies the throughput, they also applies to the I/O systems, or when an I/O system has been interfaced with the CPU. Now, let us talk about the I/O performance measurement. Here, if you recall from our early discussion in the third lecture, where we studied that an I/O system works on the principle of producer-server model. This model basically comprises an area called queue, wherein the task accumulates and it is waiting to be serviced, and the device performing the requested service is used, and this device in this model is called a server. So we can say that the producer produces task to be processed and it places it in a queue, which is in fact a first in, first out buffer. Whereas the server takes the task from the buffer and it performs them. So this model is shown over here, where you can well imagine that the response time ultimately is the time task takes from the moment it arrives in the buffer to the time server finishes the task. So with this much introduction about the overall performance measurement, let us talk about the disk I/O performance measurement. The metric of the disk I/O performance are the response time. This response time is the time to queue the information, and it is the time for the servicing of the device. Whereas the throughput is the percent of the total bandwidth. Now you can see it from this graph shown over here, which shows the relationship between the response time and the throughput of the disk I/O system. Here you can note that the minimum response time achieves only 10% of the throughput, whereas the response time of 100% throughput takes 7 to 8 times the minimum response time. Here, note this key of the curve is the area, or is the position where a little more throughput results in much longer response time. Now let us discuss how we can measure the I/O transaction time. The interaction time or the transaction time of a computer is the sum of 3 times. These 3 times are known as the entry time, the system response time, and the think time. Entry time is the time for the user to enter a command. The average value of the entry time is 0.25 seconds. However, from a keyboard it may go up to 4 seconds. The response time is the time between the user enters the command and the system responds, whereas the think time is the time from reception of the command until the user enters the next command. In order to understand this concept, let us consider an example. Here, we would like to see what happens to the transaction time as the system response time shrinks from 1 second to 0.3 seconds. Here, let us assume that when we are going to use the keyboard entry time is 4 seconds and the think time is 9.4 seconds. And for the graphics, the entry time is 0.25 seconds and the think time is 1.6 seconds. You can see it from this graph, where the upper part of the graph shows the response time for conventional use, for example, the keyboard. Here you can note that the 0.7 of response time, 0.7 comes from the shrinkage from 1 second to 0.3 seconds. This means the response time is off by 0.7 seconds. So this shrinkage in fact saves 4.9 seconds in the overall performance, which shows that there is a 34% saving. Whereas you can see it from the lower graph for the graphic applications, which saves 2 seconds, that is 70% of the total time per transaction. That is, the shrinkage in the response time results, and this in fact gives rise to an enhancement in the productivity. Once we are aware of what are the parameters to measure the performance of IOs, let us talk about the IO processor interface and what are the basic issues in this design and development of the interface. Here, the processor interface can be classified as the isolated IO, the memory mapped IO, and interrupt-based IO. I will be talking about in a moment in detail about these 3 types of interfaces, and we will see how they affect the overall performance of the system. However, while talking about the IO processor interface, we have to take into consideration the issues of IO control structures. The most commonly used IO control structures are known as the polling, the interrupts, the direct memory access, the IO controllers, and IO processors. In all these structures, the other important issues relating to the IO processor interfaces are the capacity, access time, and bandwidth. And last but not least is the interconnection. The interconnection is basically obtained by using a structure known as buses. We will be talking about the design of bus systems in detail in this discussion also. Now, let us talk about the processor interface first. as we have mentioned, that the processor interface is one which can be categorized as the isolated I/O, memory mapped I/O, and interrupts. The isolated I/O is implemented by using two different types of bus structures, such as the independent I/O bus and the common memory I/O bus. The independent I/O bus structure is shown over here in this diagram. Here you can see that the CPU is connected to the memory and to the interfaces by using two different buses. You can see it from here. One is shown as a vertical line, which is referred in this diagram as the memory bus, whereas the other one is shown over here as the horizontal line, and it is referred as the I/O bus. The implementation of this architecture requires that we should be having separate instructions for I/Os as compared to the instructions for data transfer to the memory. In order to use this structure, we use two separate types of instructions for data transfer to and from the memory or data transfer to and from the I/O devices. Usually, the standard memory data transfer instruction MOV is used for data transfer to or from the memory, whereas the in-out instruction is used for I/O devices. Whereas the second type of architecture is one which uses common bus between the memory as well as the I/O devices. As you can see it from this figure, that the central processing unit is connected to the memory modules as well as to the I/O interfaces by using a common bus. Here you can note that by isolated I/O interface, we mean that two different address spaces are allocated, one for the memory and the other for the I/O devices. Whereas the second type of memory processor interface is referred to as the memory mapped I/O. From memory mapped I/O, we mean that the address allocated both for the memory as well as for the I/O lies in the same space, which means out of the total space available, a part of the address is made available for the I/O devices. Memory mapped I/O can be implemented either by using single memory bus or by using some bus adapter which is used for bus interface. These two types of structures are shown over here in this figure. Here you can see that where we are going to use a common bus, the central processing unit is connected to the memory as well as to the interfaces for the parallel devices through a common bus. Here, as the address is also common, therefore the address is sent onto a common bus and it is identified in the address that which portion of the address is corresponding to the I/O devices and which portion of the address is allocated for the memory. The third type of processor memory interfacing is by using interrupts. The interrupt driven data transfer from the I/O devices is one, where the processor is connected with the memory as well as to the I/O devices through an I/O controller. As you can see it from here, the I/O controller box is referred to as IOC, and basically it is this I/O controller which controls the interrupts generated by the processor. As you have already studied at your undergraduate level that the interrupt-based data transfer operation is one where the microprocessor's normal operation is suspended for some time and the data transfer operation takes over the control of the bus and it performs the required operation. What is an interrupt and how it is being serviced? We can consider an example for the interrupt and its servicing from your daily routine. For example, let us suppose that you are studying in your study room where your mother calls you to bring something from the market. So this operation by your mother to stop studying and do some external job is referred to as the interrupt. How you will service this interrupt? In order to service this interrupt, you will put a flag in your book wherefrom you was reading. Then you will close the book and you will contact your mother, ask her the activity. Whatsoever activity is assigned to you, it is known as the interrupt type. That is, what type of interruption is this? So for every type of interrupt, in fact, there is some procedure which you have to follow. Now, if you have to bring something from the market, then you have to go to your garage, get your car out, go to the market and bring the things back, then park your car in the garage, hand over the things to the mother and then go back to your seat. When you go back to your seat, you unfold the book from the position where you have put the tag. This whole process of getting the information about what is to be done, how it is to be done, this is known as the interrupt service. When a similar thing happens in a microprocessor-based system by some I/O device, in fact, the microprocessor has to suspend the normal execution of the program. For this purpose, the microprocessor has to save the present status of its working onto the memory, and this operation is usually done in the stack area where the present information is stored and the control is handed over to service this interrupt. As you have noticed from this example that in order to service an interrupt, you have to follow a sequence. This sequence is stored for different types of services or different types of interrupts in different sections of the memory, and each of the procedure is referred to as the interrupt service routine. Then, depending upon the type of the interrupt, you invoke the interrupt service routine from a particular position and then you perform this operation. In the microprocessor, this is in fact equivalent to changing the contents of the program counter and jumping to a new position in the memory where the interrupt service is placed. So, and once you finish with the interrupt service, then you go back to your original position, which means the original value of the program counter is retrieved from the stack, and then the microprocessor starts executing the instructions from this position. So this shows that there is a big overhead when you have to perform the operations for the data transfer from some I/O under the interrupt control. And this is basically, as compared to other operations, it is quite time consuming. For this matter, you can look into certain practical examples from your book of undergraduate, and you can calculate the time required to service an interrupt. Another technique used to deal with I/O operations is known as the programmed I/O, or it is also known as the polling. The structure used for the polling uses a single bus structure where the central processing unit is connected to the memory as well as to the I/O devices from the common bus. However, when any external device is to perform some I/O operation, basically a small program is implemented for this purpose. The central processing unit continuously monitors the port to which the I/O device is connected or to which the I/O controller is connected. Whenever it finds a request or signal is asserted at this port and the required data is transferred either from the memory to the I/O or from I/O to the memory. Another method for the data transfer from memory to some external devices is known as the direct memory access controller method. This method is basically based on the use of a special purpose controller known as the direct memory access controller, or DMAC. Here, this DMAC is basically a processor in itself, and it controls the transfer of data from the memory to the external devices without continuous interference of the microprocessor. The system works such that initially the central processing unit sends a starting address, the direction, which means whether it is into the I/O device or it is from the I/O device to the memory, as well as the length count, that is how many bytes are to be transferred. This information is sent to the direct memory access controller, and then it issues a start command. The direct memory access controller provides the handshaking signals for the peripheral controller and the memory addresses, and it performs the handshaking with the memory. Once this operation is complete, the interrupt is generated and the control is returned back to the central processing unit. This method is indeed relatively faster as compared to the polling technique, as well as compared to the other techniques which involve the central processing unit directly for the data transfer. Another method to perform the I/O interfacing is known as the use of input-output processors. The structure used for this type of operation is shown over here. In this diagram, you can see that the central processing unit, memory, and an input-output processor is connected to one bus known as the main memory bus, whereas all devices are connected to another bus where this bus is connected to the I/O processor. This means that in this structure, the I/O processor is basically controlling the transfer or the use of main memory bus and the I/O bus. And it is this processor which looks into the memory for the command. The commands issued by the I/O processor can be divided into two phases. One is where we get an information about the target device and the address where the command is being lined. Whereas the second phase of this is the opcode, which shows what is to be done. The address, which means where to put the data, and the count, which identifies how many bytes are to be placed, and the other information is about some special request if there is any. Now, with this much discussion today, we have observed that the disk industry is growing rapidly. It is improving with an improvement in the bandwidth as 40% per year, and the areal density is increasing at the rate of 60% per year. Moreover, we have also discussed that the value of the faster response time is always used for the enhancement of the performance of I/O-based systems. Then, today we also discussed what are different techniques which are used for I/O processor interfaces. In this case, we have discussed different type of I/O bus structures. Now today, with this much discussion, I will stop over here, and next time, inshallah, we will discuss in details what are the I/O interconnections and how their performance can be measured. Till then, Allah Hafiz.